In topology, two continuous functions from one topological space to another are called homotopic equals same, similar, and tau omicron pi omicron sigma equals place, if one can be continuously deformed into the other, such a deformation being called a homotopy between the two functions. A notable use of homotopy is the definition of homotopy groups and cohomotopy groups, important invariants in algebraic topology. In practice, there are technical difficulties in using homotopies with certain spaces. Algebraic topologists work with compactly generated spaces, CW complexes, or spectra. Formal definition. Formally, a homotopy between two continuous functions f and g from a topological space X to a topological space Y is defined to be a continuous function h, x times 0, 1, y from the product of the space X with the unit interval 0, 1 to y such that, if x then h equals f and h equals g. If we think of the second parameter of h as time, then h describes a continuous deformation of f into g. At time 0 we have the function f and at time 1 we have the function g. We can also think of the second parameter as a slider control, that allows us to smoothly transition from f to g as the slider moves from 0 to 1, and vice versa. An alternative notation is to say that a homotopy between two continuous functions f, g, x, y is a family of continuous functions ht, x, y for t, 0, 1, such that h0 equals f and h1 equals g, and the map ht is continuous from x times 0, 1 to y. The two versions coincide by setting ht equals h. It is not sufficient to require each map ht to be continuous. The animation that is looped above right provides an example of a homotopy between two embeddings, f and g, of the torus into R3. X is the torus, y is R3. F is some continuous function from the torus to R3 that takes the torus to the embedded surface of a donut shape with which the animation starts. G is some continuous function that takes the torus to the embedded surface of a coffee mug shape. The animation shows the image of ht as a function of the parameter t, where t varies with time from 0 to 1 over each cycle of the animation loop. It pauses, then shows the image as t varies back from 1 to 0, pauses, and repeats this cycle. Properties continuous functions f and g are said to be homotopic if and only if there is a homotopy h taking f to g as described above. Being homotopic is an equivalence relation on the set of all continuous functions from x to y. This homotopy relation is compatible with function composition in the following sense. If f1, g1, xy are homotopic, and f2, g2, yz are homotopic, then their compositions f2, f1 and g2, g1, xz are also homotopic. Homotopy equivalence. Given two spaces x and y, we say they are homotopy equivalent, or of the same homotopy type, if there exist continuous maps f, x, y and g, yx such that gf is homotopic to the identity map idx and fg is homotopic to idy. The maps f and g are called homotopy equivalences in this case. Every homeomorphism is a homotopy equivalence, but the converse is not true. For example, a solid disk is not homeomorphic to a single point, although the disk and the point are homotopy equivalent. As another example, the Mobius strip and an untwisted strip are homotopy equivalent but not homeomorphic. Spaces that are homotopy equivalent to a point are called contractible. Intuitively, two spaces x and y are homotopy equivalent if they can be transformed into one another by bending, shrinking and expanding operations. For example, a solid disk or solid ball is homotopy equivalent to a point, and R2- is homotopy equivalent to the unit circle S1. Null homotopy. A function f is said to be null homotopic if it is homotopic to a constant function. For example, a map f from the unit circle S1 to any space X is null homotopic precisely when it can be continuously extended to a map from the unit disk D2 to X that agrees with f on the boundary. It follows from these definitions that a space X is contractible if and only if the identity map from X to itself, which is always a homotopy, equivalence, is null homotopic. Invariance. Homotopy equivalence is important because in algebraic topology many concepts are homotopy invariant, that is, they respect the relation of homotopy equivalence. For example, if X and Y are homotopy equivalent spaces, then, if X is path connected then so is Y. If X is simply connected then so is Y. The homology and cohomology groups of X and Y are isomorphic. If X and Y are path connected, then the fundamental groups of X and Y are isomorphic, and so are the higher homotopy groups. Isomorphic to pi1, where f xy is a homotopy equivalence and x0x. An example of an algebraic invariant of topological spaces which is not homotopy invariant is compactly supported homology. Relative homotopy. In order to define the fundamental group, one needs the notion of homotopy relative to a subspace. These are homotopies which keep the elements of the subspace fixed. Formally, if f and g are continuous maps from X to Y and K is a subset of X, then we say that f and g are homotopic relative to K if there exists a homotopy H. X times 0, 1, Y between f and g such that H equals f equals g for all k and t, 0, 1. Also, if g is a retract from X to K and f is the identity map, this is known as a strong deformation retract of X to K. When K is a point, the term pointed homotopy is used. Groups. Since the relation of two functions f, g, x, y being homotopic relative to a subspace is an equivalence relation, we can look at the equivalence classes of maps between a fix x and y. If we fix x equals 0, 1, n, the unit interval 0, 1, crossed with itself n times, and we take its boundary as a subspace, then the equivalence classes form a group, denoted ∀n, where y0 is in the image of the subspace. We can define the action of one equivalence class on another, and so we get a group. These groups are called the homotopy groups. In the case n equals 1, it is also called the fundamental group. Category. The idea of homotopy can be turned into a formal category of category theory. The homotopy category is the category whose objects are topological spaces, and whose morphisms are homotopy equivalence classes of continuous maps. Two topological spaces X and Y are isomorphic in this category if and only if they are homotopy equivalent. Then a functor on the category of topological spaces is homotopy invariant if it can be expressed as a functor on the homotopy category. For example, homology groups or a functorial homotopy invariant. This means that if f and g from X to Y are homotopic, then the group homomorphisms induced by f and g on the level of homology groups are the same. Hn equals hn. Hn for all n. Likewise, if X and Y are in addition path connected, and the homotopy between f and g is pointed, then the group homomorphisms induced by f and g on the level of homotopy groups are also the same. ∀n equals ∀n. ∀n. Time-like. On a Lorentzian manifold, certain curves are distinguished as time-like. A time-like homotopy between two time-like curves is a homotopy such that each intermediate curve is time-like. No closed time-like curve on a Lorentzian manifold is time-like homotopic to a point. Such a manifold is therefore said to be multiply connected by time-like curves. A manifold such as the three-sphere can be simply connected, and yet be time-like multiply connected. Lifting property. If we have a homotopy H, x times 0, 1, y and a cover P, y, and we are given a map H0, x, y such that H0 equals PH0, then we can lift all H to a map H, x times 0, 1, y such that PH equals H. The homotopy lifting property is used to characterize fibrations. Extension property. Another useful property involving homotopy is the homotopy extension property, which characterizes the extension of a homotopy between two functions from a subset of some set to the set itself. It is useful when dealing with cofibrations. Isotopy. In case the two given continuous functions f and g from the topological space X to the topological space Y are embeddings, one can ask whether they can be connected through embeddings. This gives rise to the concept of isotopy, which is a homotopy H in the notation used before, such that for each fixed T, H gives an embedding. A related, but different, concept is that of ambient isotopy. Requiring that two embeddings be isotopic is a stronger requirement than that they be homotopic. For example, the map from the interval -1, 1 into the real numbers defined by f equals -x is not isotopic to the identity g equals x. Any homotopy from f to the identity would have to exchange the endpoints, which would mean that they would have to pass through each other. Moreover, f has changed the orientation of the interval and g has not, which is impossible under an isotopy. However, the maps are homotopic. One homotopy from f to the identity is h -1, 1 times 0, 1 -1, 1, given by h equals 2yxx. Two homeomorphisms of the unit ball which agree on the boundary can be shown to be isotopic using Alexander's trick. For this reason, the map of the unit disk in R2 defined by f equals is isotopic to a 180-degree rotation around the origin. And so the identity map and f are isotopic because they can be connected by rotations. The un knot is not equivalent to the trefoil knot since one cannot be deformed into the other through a continuous path of embeddings. Thus they are not ambient isotopic. In geometric topology, for example in knot theory, the idea of isotopy is used to construct equivalence relations. For example, when should two knots be considered the same? We take two knots, K1 and K2, in three-dimensional space. A knot is an embedding of a one-dimensional space, the loop of string, into this space. And this embedding gives a homeomorphism between the circle and its image in the embedding space. The intuitive idea behind the notion of knot equivalence is that one can deform one embedding to be another through a path of embeddings. A continuous function starting at t equals 0 giving the k1 embedding, ending at t equals 1 giving the k2 embedding, with all intermediate values corresponding to embeddings. This corresponds to the definition of isotopy. An ambient isotopy, studied in this context, is an isotopy of the larger space, considered in light of its action on the embedded submanifold. Knots K1 and K2 are considered equivalent where there is an ambient isotopy which moves K1 to K2. This is the appropriate definition in the topological category. Similar language is used for the equivalent concept in contexts where one has a stronger notion of equivalence. For example, a path between two smooth embeddings is a smooth isotopy. Applications. Based on the concept of the homotopy, computation methods for algebraic and differential equations have been developed. The methods for algebraic equations include the homotopy continuation method and the continuation method. The methods for differential equations include the homotopy analysis method.